Hello everyone. Today I'm going to talk about quantum circuit complexity and in particular our recent work on QAC0 circuits with barely superlinear ancillae. I am Yangjing. This work is collaborated with Anshu, O, and Yao. In quantum computation, quantum circuits are perhaps the most natural models of quantum computation and where when we want to compute Boolean functions, we can feed the inputs to the left of the circuit along with some ancillary qubits initialized to the zero state. Then we can apply several layers of quantum gates as quantum computation, and in the final step, we can measure one single qubit of the circuit in the computational basis and take that as the computational outcome. In quantum circuit complexity, we are concerned about lower bounds on the depth and the size for computing some Boolean functions such as majority, parity, and etc. One simple observation shows that the axial lower bound is a good proxy for the size lower bound. So in this work, we will give axial lower bounds. For local quantum circuits, there is already a very powerful argument which is called the light cone argument. The general idea behind a light cone argument is as follows. Suppose we have a circuit which consists of only two qubit gates and has depth d. Then the output of this single qubit will be determined by only the qubit in its light cone, which consists of only 2 to the power of d input qubits. So as a lower bound, because most non-trivial Boolean function, the outputs will depend on all of the n inputs. We have 2 to the power of d is at least n. So we can get a log n dash lower bound for local quantum circuits computing almost every non-trivial Boolean function. In this work, we consider quantum circuits with unbounded fine gates. And as in this example, one Control Z gate acts on all the qubits and thus the output already depends on all the inputs. In this case, of course, the light cone arguments will fail. So we ask, what are the quantum circuit lower bounds beyond light cones? To ask this question, we will first look back at classical shallow circuits, which there are NCI circuits and ACI circuits. The NCI circuits are defined to be the circuits with bounded line gates that act on only two qubits and has depth log n to the power of I. ACI circuits are defined to be the circuit with unbounded line circuits where you can compute the and or all of arbitrary number of inputs and also has depth log n to the power of I. And to the right is an illustration of a classical circuit which computes the XOR function. It is immediate that a single unbounded fine-in the AND gate can be simulated by bounded fine-in gates with log n layers. So the relation between NC circuit and AC circuit is that while NCI is contained within ACI, ACI is contained within NCI plus 1 because large unbounded gates can be simulated by log n layers of small bounded fine gates. An important result in computational complexity is about the parity functions, which computes the bitwise XOR of the n inputs. Obviously, this parity function can be computed by an NC1 function circuit because we can compute the parity of n bits as in the circuit shown in the right with log n layers. An important result by Hastad shows that parity cannot be computed by AC0 circuits using the famous switching lemma. This result shows that AC0 is not equal to NC1 because NC1 can compute the parity function and AC0 cannot. And this is the field of the non-trivial unconditional separations in classical computational complexity. In this work, we focus on QAC0 circuits, which is a quantum generalization of AC0 circuits first introduced by Moore in 1999. The QAC0 circuit consists of CZ gates of arbitrary size and arbitrary single qubit unitaries. The CZ gate is defined to be the gate that when act on X applies a phase flip if X is the O1 and does nothing otherwise. This is indeed a quantum generalization of the unbounded finite AND gate. And the arbitrary single qubit unitaries are quantum generalizations of the NOT gates in AC0 circuits. The first question we may ask is that are QAC0 circuits at least as strong as AC0 circuits? Although this question might seem obvious, the answer is not necessary and we don't know the answer because we cannot copy quantum states. And while in quantum classical circuits, the output of a single gate can be fed into arbitrarily many other gates, in quantum computation, the output of a quantum gate can be fed only at one another quantum gate, because quantum states cannot be copied. Another important question is, can QAC0 circuits compute parity? Our conjecture is that QAC0 circuits as AC0 circuits cannot compute parity with polynomial size. Currently, the best known circuit to compute parity is by Rosenthal in 2021, which shows that there exists a DAS7 circuit with exponential ancilla that computes parity in the average case. We also have lower bounds, which shows that to compute parity exactly, we need at least a linear lower bound on the ancilla. And to compute parity exactly with DAS2 circuits, this is impossible even if we have an unlimited number of ancillas. This impossible result was generalized to the average case in 2021, and last year in 2024, in the breakthrough result, it has been shown that to compute parity in the average case, we need at least n to the power of 1 over d ancilla. This is the first polynomial lower bound on the ancilla for computing parity with QAC0 circuits. In this work, we give new lower bounds on this problem and show that for any QAC0 circuit with stats D and ancilla size A to compute parity and with an average case error that is slightly smaller than a half, the ancilla size must be lower bounded by n to the power of 1 plus exponential minus d. This lower bound is barely superlinear, and this is why we put barely superlinear in our title. Although this lower bound might seem still far away from our conjecture that any polynomial sized QAC0 circuits cannot compute parity, surprisingly, another result shows that if we can improve our lower bound a little bit and get any lower bound of the form n to the power of 1 plus exponential minus od, for example, we can replace the d in the exponent into d over log d, then this kind of lower bounds can be boosted to show that parity cannot be computed by any QAC0 circuits with any polynomial size. To illustrate our results on a line where the points on the lines are ancilla lower bounds and our ultimate goal is to prove an arbitrary polynomial lower bound, Previous results have shown that to compute parity in the average case, we need at least n to the power of 1 over d ancilla, and to compute parity in the exact case, we need at least omega n ancilla. Our work points two new points on this line, where the left point shows that towards our goal, we are already here, and we have shown a barely superlinear lower bound. The right point shows that actually to reach our goal, we only need to make a little improvement, and then the lower bound can be boosted to the ultimate goal. Some other results. First, we remark that our lower bound holds for not only the parity function, but many other Boolean functions such as majority and mod k. And also, our lower bound holds for other quantum tasks such as quantum state synthesis and channel synthesis. Now, to proceed to our technical results, I need to introduce the notion of approximate degree of a quantum operator. We say that an operator has degree d if this operator P can be written in terms of the sum of the operators Pi, where each Pi acts non-trivially on at most d qubits. Also, the approximate degree of P is defined to be the minimum degree of an operator Q that epsilon approximates P in the spectrum distance. Our main technical theorem states that for U to be the unitary implemented by a QAC0 circuit with density and A ancilla, and then let A be any measurement operator with degree L. Then the Heisenberg-evolved measurement operator U dagger AU has an approximate degree upper bound, which is n plus a to the power of 1 minus exponential minus d times L to the power of exponential minus d. This theorem states that if we want to apply a quantum measurement after a QAC0 circuit and the measurement operator has low approximate degree, then the overall effect described by the Heisenberg-evolved measurement operator U dagger AU also has a low approximate degree. As a corollary, since if when we are computing Boolean functions, we only measure one single qubit at the final step, the measurement operator A has degree 1. So if we let P to be the polynomial that describes the probability that a QAC0 circuit outputs 1, then we can show that the approximate degree of P is also upper bounded by this single term with L equal to 1. In contrast, the approximate degree of parity is linear. So as long as the ancilla size A is barely superlinear, then this approximate degree remains smaller than n, so it cannot compute parity. We remark that this result generalizes the approximate degree upper bounds for linear size AC0 circuits, and this is tight because it has been proved in the same work that there exist linear size AC0 circuits that has approximate degree approaching this lower bound. Our work is similar to that of MPVY24, which gives a polynomial ancilla lower bound for computing parity, and here we sketch the main differences. We proved that the Heisenberg-evolved measurement operator is low degree, while in their work they proved the choice state of the single output channels is low degree. One important difference is that in our work we use spectronorms for approximation, while in MPVY24 they use Frobenius norm. As a result, we need more refined approximation techniques, and we cannot directly delete the large CD gates as they did in their work. In construct, we will replace large CD gates with some low-degree approximators that have low approximate degree. Also, the spectrum is more friendly when tackling with ancillae. So our degree upper bound depends on the ancillae size in a better way than they do. Now I can briefly explain the main ideas on how to prove the approximate degree upper bounds for QAC0 circuits. And I will start with the simplest case where we have one single layer of small gates, each acting on at most, say, T qubits. In this case, we will show that the approximate degree of U dagger AU is upper bounded by the approximate degree of A times T by a light cone argument. This is because for any unitary that does not touch U, then U1 dagger and U1 will cancel out with each other because they multiply to identity. So only the unitaries that touch A will remain. So the approximate degree of U dagger AU is limited by within the light cone of A, which is approximate degree of A times T. The hard case comes when we have large Toffoli gates, and this is where we use low degree approximations. First, recall that the CD gate, when applied on some input state, will apply a phase flip only if X is the odd one state and does nothing otherwise. So when written in matrix form, CZN is exactly a diagonal matrix with all the entries to be 1, except one single entry, which is -1. So CZN equals to identity minus 2 times the O1 state. Recent work on approximation theory shows that approximate degree of the tensor product of n single qubits is upper bounded by square root n. As a corollary, this shows that large CD gates has relatively small approximate degree because the identity operator has degree 0 and the all one state has degree square root n. We can prove that the approximate degree of CZN is upper bounded by square root of n. So when we apply this upper bound to QAC0 circuits, consider we have a layer of very large CD gates and each UI acts on, say, at least T qubits. Then the first observation is that the number of gates in this layer is upper bounded by n plus a over t because each gate is large enough. However, the approximate degree of each UI is upper bounded by square root t by the results of the previous slide. So combining this, we can show that approximate degree of the single layer is upper bounded by the sum of the approximate degrees of each gate, and this yields n plus a over square root upper bound on the approximate degree. Applying this to the approximate degree of U dagger AU, we will show that the approximate degree of A will get increased by a term only of n plus a over square root t. Now it's time to combine these two cases together and assume we have a layer of different size gates. We will split these gates into two sets where US is a set of small gates, each acting on at most T qubits, and UT are the large gates which act on at least T qubits. By the light cone argument, we know that the small gates in US will multiply the approximate degree by a factor of at most t, and the large gates will increase the approximate degree by at most n plus a over square root t. So combining the upper bound, the approximate degree upper bounds in the previous slides, we know that the approximate degree of u dagger au is upper bounded by L times t plus n plus a over square root t, where a is the approximate degree of a. Optimizing over t, we see that the approximate degree of u dagger au is upper bounded by the original degree to the power of 1/3 times n plus a to the power of 2/3. This is what we do with a single layer of quantum gates. And we need to repeat this upper bound d times because a QAC0 circuit can have a constant d layer of quantum gates. So originally the approximate degree of A is L. After one layer, by using the upper bound from the previous slides, we know that the approximate degree is upper bounded by n plus a to the power of 2/3 times L to the power of 1/3. Then, using another instance of the previous upper bound, we can get an approximate degree upper bound, which is n plus a to the power of 8/9 times L to the power of 1/9. And we repeat this process for all the d layers to get the approximate degree n plus a to the power of 1 minus 3 to the power of minus d times L to the power of 3 minus to the power of minus d. And this is exactly the approximate degree upper bound we have stated in our main technical theorem. Now we can apply our approximate degree upper bounds to the task of computing Boolean functions. We will show that if P is the polynomial that describes the probability that a QAC0 circuit outputs 1, then the approximate degree of P has this same upper bound. The first step of the proof is to write out the exact formula of Px, and recall that to compute a Boolean functions with QAC0 circuits, we will prepare the input along with some ancilla states initialized to all 0, and then apply the QAC0 circuit, and finally measure one single qubit in the computational basis. So rearranging this formula, we will see that if the square represents the matrix of the operator u dagger au, where a is the measurement on the first qubit, then p is exactly sum of the diagonal entries of this Heisenberg-evolved measurement operator. So matrix norm inequalities shows that the approximate degree of P is upper bounded by the approximate degree of this Heisenberg-evolved measurement operator, which has approximate degree lower bound of n plus a to the power of 1 minus 3 to the power of minus d, and this is what we want. This approximate degree upper bound can directly be used to prove worst-case hardness results for computing Boolean functions. For example, we already know that the approximate degree of parity function with error up to 1/3 is linear. So for a QAC0 circuit with barely superlinear ancillae, it cannot compute parity and with worst-case error that is strictly better than 1/3. And the proof is obvious because if on a contradiction there exists such a QAC0 circuit, then we can prove that the approximate degree of parity is sublinear, and this leads to a contradiction. This argument only relies on the fact that the approximate degree of the Boolean function f is linear. So this argument works for not only the parity function, but also other functions such as majority and mod k. Also, the constant 1 over 3 can be improved to 1 over 2 with some easy error reduction techniques. We can also prove average case Hart results similar to that of MPVY24. That is, any QAC0 circuit that computes parity with a non-trivial error in the average case must use at least n to the power of 1 plus exponential minus d ancilla. The proof is almost identical because we have proved the approximate degree upper bounds in the spectral norm, and in their proof, they only require the smaller Frobenius norm error. Approximate degree upper bounds can also be used to other tasks in quantum computation, such as quantum state synthesis and quantum channel synthesis, because in all these cases, we can apply the same techniques and derive similar approximate degree upper bounds. The final topic I want to talk is the observation that any minor improvement to our lower bound can be boosted to prove that parity cannot be computed by QAC0 circuits of any polynomial size. And the proof is as follows. Suppose there exists a constant C and a family of QAC0 circuits that compute parity n with n to the power of C ancilla. Then, for any k, we will construct a circuit family with dash CDK and ancillar size n to the power of 1 plus exponential minus k. And in the third step, since C and D are constants, we can choose k a constant but large enough such that 2 to the power of minus k is strictly smaller than exponential of minus small o CDK. And this leads to a contradiction because we have used too few qubits to compute the parity function. So following, I will explain how we construct such a family with that CDK and ancilla only n to the power of 1 plus exponential minus k. The idea behind this is actually very simple, because if we have a circuit UN that computes the parity of n bits using density and n to the power of c ancilla, then we can combine two instances of such circuits to compute the parity of m equals to 2n bits, but with an ancillar size only strictly smaller than m to the power of c. Thus, this decreases the exponent on the ancillar size. Instead of repeating un 2 times, we can repeat it n times to get better parameters, and we can construct a circuit with dash 2D that computes the parity of m equals to n squared input bits, and the ancillar size is only n to the power of c plus 1, which is m to the power of c plus 1 over 2. So with this construction, we have effectively reduced the exponent in the ancillar size from c to c plus 1 over 2. That is, we halved this exponent. So by constructing a tree-like circuit, actually we can, in constant dash, reduce the exponent from any constant c to a constant 2. This shows that with any circuit that computes parity with n to the power of c ancilla, we can construct a circuit that computes parity with m to the power of 2 ancilla. And recall that our goal is to make the exponent as small as 1 plus 2 to the power of minus d. So we will use a more refined construction, where in each layer we compute the parity of different number of inputs. And in particular, in the case layer, we will compute the parity of n to the power of 2 to the power of k inputs. And a careful calculation shows that this achieves our best ancilla size, which is m to the power of 1 plus 2 to the power of minus k. So in summary, we have proved that for QAC0 circuits, the approximate degree is upper bounded by something barely sublinear, and this shows that to compute parity, majority, and mod k requires ancilla size that is barely superlinear. We also show that to prove the conjecture that QAC0 circuits cannot compute parity, we only need a slightly better upper bound that we get in our work. For open problems, of course, first we want to know whether indeed QAC0 circuits cannot compute parity. We can also ask the more general question about the exact approximate degree of QAC0 circuits. This is also open for AC0 circuits.